Welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing Landau-Ginzburg theory. Let's quickly recap what we have done. We discussed in the last lecture issues with Landau theory, and we came up with a fix which is called the Ginzburg-Landau theory. What is the central input into Ginzburg-Landau theory is the fact that we have to include fluctuations both in space and thermal fluctuations. And the problem we are trying to address is the fact that Landau theory gives the same critical exponents irrespective of symmetry and spatial dimension. So we introduced the space dependent field phi of x, which transforms correctly under the symmetry transformation, and the emergent field phi must also be sensitive to the fact that there must be there is some ultraviolet cutoff or some momentum cutoff which is given as inverse of this space cutoff. So associated with each field phi, we came up with some functional which describes its energetics, and this functional itself is an integral of some kind of density, and this density depends on the value of the field at the point, its gradients, etc. And the statistical weight is proportional to e to the minus phi, and so the partition function was was written as a functional integral. The density is chosen so that all the conditions of analyticity, symmetry, and phenomenology, etc. are incorporated, right? So we saw in the last lecture that we can indeed capture some physics of some systems such as superconductors, etc. by using Ginzburg-Landau theory. So this is where we are, and important things that I did not discuss in the last lecture, or I relegated to this lecture, is how do we calculate with the Landau-Ginzburg theory, right? In particular, what do we actually mean by this thing called as the functional integral, right? This is what we will spend most of our time in this lecture, okay? All right. So let's discuss this ON vector Landau-Ginzburg theory. So what we have is we have an emergent field which is an n component real vector field phi of x written in vector form here, that transforms as the following. You give me some R which is some n by n orthogonal matrix in this group ON. You give me any field here, I will give you a new field which is the transformed field. So what I will do is I will simply rotate every vector by this R. Okay, so that is what I will do. Vector at every point by this R. Okay, and the Landau-Ginzburg action functional S is written as S of phi, which is integral of some density, and this density, the way we introduced it was we are using the simplest Landau-Ginzburg form. It is y by 2, y is a coupling constant or some constant, they are parameters, and this is gradient phi square, and we discussed what this gradient phi square means. So it is both a spatial scalar as well as a ON scalar, and then this is the usual Landau term. And please note that from here on we are going to use a slightly different notation for reasons to connect with more common literature, if you like, right? So we don't have A, B and so on. So B has been changed to U and there is no A, and I had mentioned a couple of lectures back that you can absorb all these things into the definition of your units and variety of things. In fact, we will even change notation even later depending on what physics we are after, as you will see. So yeah, so that is the small point to be noted. Okay, so this y and u are some non-negative parameters, and t is a dimensionless coupling constant which will tune our systems towards criticality and so on. Okay, now this L is written with the symmetry in place, right? So you don't have any symmetry breaking field. Suppose I had a symmetry breaking field H, which I may want to add to explore some physics, then I will change this density by a term which tells me how this emergent field is interacting with the symmetry breaking field, and the most natural thing to write down is minus H dot phi, right? So this is very straightforward. Okay, so you give me some functional, some inner action function density like this, L density like this, then I'll write the partition function, I'll compute the functional. Okay, so this should be a script S. I'll compute this functional and I will do this integral over the space of functions, and this is a functional integral, which is what we are trying to understand, what we need to how we give meaning to the statement. So again, I have to emphasize this cannot be overemphasized. You see, when I write this theory like this, nowhere does this ultraviolet cutoff explicitly appear, right? So up to, if you think that this is the definition of the theory here, the ultraviolet cutoff does not appear anywhere explicitly. But you have to remember that there is an ultraviolet cutoff in the theory. It's very important, as you will see later, right? So this is what I'm just flashing here. You must remember that the theory has an ultraviolet cutoff. Okay. Okay, what do we do now? So I want to show you how to define and evaluate such functional integrals. So a natural place to do it would be to start by evaluating some simple known integrals, right? Okay, so let's start with that. To understand what do we mean by a functional integral, we must take a practical approach. That's what I'm emphasizing in the point here. Functional integrals are somewhat difficult to define mathematically, right? We will sidestep the mathematical sort of finesse on this, and we will take a more practical definition which allows us to do some computations and get some results, right? So we are going to go with a more pragmatic operational definition, and for this, for the definition to work and for us to do computations, I have to revise some simple integrals that all of us know very well. Okay. So the most important result we need to define functional integral is this result here, which is that integral minus infinity to infinity of e to the minus a x square, this is on real numbers, is square root pi by a, right? So this is called the Gaussian integral, and I'm sure that you have seen this evaluated in many courses before. So that is the most important result. Now it turns out that we need a small variant of this. So small variant of that is, we are going to introduce two variables, two real variables. So it's like a two-dimensional space if you wish. So there is dx and dy, and I'm going to evaluate e to the minus a x square plus y square. So if I now do integral minus infinity to plus infinity on x and y both, then it's just the square of this result, and that's just pi by a. Okay. This is morally the result that we need, but we need it in a slightly different form. What is the form that we need? What I'm going to do is I'm going to introduce a complex variable, right? The complex variable z is equal to x plus iy, and I'm going to transform this integral into this complex variable. So x square plus y square becomes e to the minus a z star z, that's obvious. And this is the integration measure. So this must be thought of as the area element dx dy. So you must compute the area element between dz star and dz, and that you can do as a small exercise and show that this dz star dz by 2i will be dx dy. Okay. So this is the main result that we need. If we know this, my claim is that we can compute functional integrals once we define them. Okay. All right. So in case you feel that some of this is rusty, please revise this because these results will be very important for us. Okay. So the first thing we need to do is we need to very carefully define what our emergent fields are. We did this in the last lecture. We'll do this again in this lecture very carefully. So the idea is the following. my fields are defined in a continuum arena. So my set of points that I have are form a continuum, and so it's in a box, a cubic, d-dimensional cubic box of side L. So the volume is L to the d, and I have periodic boundary conditions for all my fields. Okay. So now this phi of x is defined using Fourier transform. So you now see what we are doing is we are defining phi of x using Fourier transforms in the following way. Remember that there was this ultraviolet cutoff. I am going to take all the momenta. So let me show you the picture here. So this is the momentum space, right? And this is k1 and k2. I am doing in 2 dimensions, and the allowed set of momenta, why do I say allowed? Because I need periodic boundary conditions. The ones that allow this phi of x to be periodic in this box have only these k's allowed in the Fourier transforms. What are the k's? It's 2 pi by L times integer, 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 right? And these points here, the grid, the points of the grid are the allowed k points. So if I take the distance between any two k points here, that will be 2 pi by L. So the volume element here will be, in this case, since it's 2 dimensions, it will be area element. Area is the volume in 2 dimensions, and so 2 pi by L square. If it is in d dimension, the hypercube or the d-dimensional hypercube formed by this little chunk here will be 2 pi by L to the power d. Okay. So now the point is that I am only keeping the k within this circle, or the in the higher dimension some sphere of radius lambda. I am not going all the way to, so this is z, they are integers, and mod k less than or equal to lambda, right? So only the things in the shaded region, only the points that, for k points that fall within the shaded region, are the allowed momenta in our system. So this will ensure that the field phi of x has no fluctuations on scale, length scale smaller than LC, right? Now the important point to observe here is that if I am now in some finite volume V, then the number of k points within this is of course large, because V is very large itself. But the important thing is that there are a finite number of them, however large. Okay, that's my first observation. I will make this point again momentarily. The next thing to remember is that our phi of x is a real field, right? So we have discussed that in the previous slides. It's a real valued, and because phi of x is real valued, this phi k are not all independent. So in fact phi minus k, so if I have this k here, the value of phi there and the value of phi at minus, which is somewhere here, they will be related to each other by this result. So phi minus k will be phi star k, right? Complex conjugate of phi k. So phi minus k will be complex conjugate of phi k. Okay, so this will ensure that this field phi of x is real. Okay. Again, I want to emphasize this point I made just a moment back. So if you keep volume is finite, there are only a finite number of k points, and the number of k points is of course proportional to L to the d, lambda to the d. That's easy to see. Lambda to the d times some, so if it is 2 dimensions, it will be like pi times lambda to the d will be the area of this circle. And each of these things is taking 2 pi by L square. So if I take lambda pi times lambda square divided by 2 pi by L whole square, then I'll get something proportional to L square lambda square. So I'll get that many points inside here. So the important thing is that there are a finite, albeit large number of points in this sphere. Okay, all right. Okay. Now I have prepared all the required background to define what a functional integral is. Okay. So let me go ahead and do that here. So it turns out that for us to define the functional integral and evaluate it, it turns out that it is very useful to start with a special case of the Ginzburg-Landau theory, where u and the external field are both 0. Okay, it's not essential, but it's at least pedagogically useful. Okay, so let's start with this. So my S of phi is integral of this density, and my partition function is a functional integral over exponential of this action. Okay, all right. Now, first thing we'll do is we will take S of phi that's written here as an integral over real space and convert it to terms associated with the Fourier components of phi. Okay, this is an elementary exercise, and I think you should, if you're not able to see this immediately, you must pause the video and work through this, right? And or you could just take it for granted now, but you definitely should work through this. So S of phi is written in this fashion. So it will be 1/2 y times k square. So this k square comes from the fact that this gradient, when you take the gradient of a Fourier transform, it will pull down a momentum, right? So that's how this k square will show up, plus t times phi dot phi. So if you write it in component form, this phi star k dot phi k will be contracted over the indices, right? So this will be phi alpha, right? So that's what you will end up getting. Okay, so this is the result. Okay, so the important thing is that this sum has, at a finite volume, if the periodic box of volume V, there are a finite number of k points, large but finite. So how can I visit all possible functions phi of x? Remember, I want to integrate over the space of functions. So if I vary all possible values of phi k, then I will be able to visit all possible functions, right? So that is our clue to defining the functional integral. So the functional integral is defined as, this quantity is defined as, okay, don't worry about the square root, I'll explain it in a minute. I am taking the integral of the alphath component of the kth momentum vector, the phi alpha k. So this is the alphath component of the Fourier transform at momentum k, and I am integrating all of these quantities. So it's a multi-dimensional integral e to the minus s phi. Okay, so I'm doing a big multi-dimensional integral over each Fourier component as well as the component of the vector in its space. So for each component direction in the ON space, there is a Fourier component. So that is phi alpha of k, means it is the Fourier component at the momentum k, right? So this is the Fourier transform of the alpha component of the ON vector. So each momentum is like a complex variable, and I am integrating this over that complex variable. That's what I am doing. Okay, and you see I am now introduced this this bracket alpha. So this is not summed, repeated indices are not summed here, right? So this is product over all the components and product over all the k's. So that will exhaust for you all the possible Fourier components, both in momentum and internal ON internal component, right? Multiply by e to the minus s. So what I am doing is I am defining the functional integral as a multi-dimensional integral over the Fourier components of my field. That is what I am doing. That is my definition. Okay. Now this is very nicely defined because these are just, it's a huge, very high dimensional integral, but it is just a multi-dimensional integral. Okay. So first question, what is the square root doing here? Okay. So first point I already made, which is that integrating over all phi of x is like integrating over all the Fourier components phi k for each component of phi, each ON component of phi. So the square root appears because when I am doing this integral, I am treating each k point and each component, each on component at each k point as an independent complex number. But we know that they are not independent because phi minus k is equal to phi star k. So because I made them independent now, I am double counting. I am double counting all the k points. So for every plus k there is a minus k, and if you see the condition at k equal to 0, it says that phi of 0 must be equal to phi star 0. So the phi at 0, k equal to 0 must only be a real number, but I am treating it as a complex number. So I am double counting, so I have 2 degrees of freedom. So because I am double counting, I have to take a square root of this, right? That is why the square root is there. Okay, so in some sense, by taking the square root, I have reduced the thing to number of independent components of phi alpha k. So this is what has gone into this calculation. Okay. Okay, now it turns out that you can actually do this integration. So what you do, you take this S of phi. Remember in the last slide, we put S of phi in Fourier space, right? And that's just a sum over these things. So what I can do is I write this as a sum over, I write this S of phi as a sum over k less than lambda of these things. Now what I can do, at each k point for each component of on component of phi alpha k, I can do this integral separately. So this is just an integral of the kind dz star dz by 2i e to the minus a z star z. It's exactly that kind of integral. But I know the answer for that integral from the previous slides that we discussed. So what will happen, for at any k there are n components. Each component will give me 2 pi divided by y k square plus t, which is just, this is a now. So that's why I get this pi by a, and it's complex, and that to the power n because I have n components. This alpha will go from 1 to n. So therefore I get this, and I take a product of, there are many, but I can take product of each one of them. So I'm just taking a product of a large number of quantities like this, right? A product over k and so on. And this I have taken the square root, and so if I want to take the square root, I can do this and take n by 2 here. So friends, we have just evaluated this functional integral. We have defined the functional integral and evaluated it, and remember, we are able to evaluate this so nicely because we set u equal to 0 and h is equal to 0, right? But you will realize after a little bit that is enough for us to make a lot of progress. Okay, so we have evaluated this. Okay, what can we do with this? So I have got the partition function now, but partition function usually doesn't do the trick for me. I need to get the free energy. So this is the partition function which was evaluated in the last slide, and to get to the free energy, I just take the log of this partition function. When I take the log of the partition function, okay, so what now happens is this log of product is sum of logs. So this becomes n by 2 shows up here, log of this quantity, then minus sign will invert this. So you get y k square t by 2 pi. Okay. Now this is a sum over all the k points in that picture that I showed. So basically it's sum over all these k points, right? It's sum over all these k points inside this. So what we can do is we can convert that to an integral. That's what is done here. So what we do is, suppose I put a ddk, so that the volume of that is 2 pi by L whole to the power d, and I have to take the inverse version of that outside. So that will give me v by 2 pi to the d, and this just becomes the integral, and so I end up getting this integral. So what you see now is a very, very nice result which says that the free energy, total free energy, is correctly extensive. It's proportional to the volume of the system times an integral of this function evaluated in momentum space in that region that we discussed. So it's integral from in the region where mod k is less than or equal to lambda. So this is something we should be very happy about, because this is turning out to be something meaningful at least. Okay. And second thing is that what we can do is if you want to go to the thermodynamic limit, then what happens, this V, you can divide F by V and you can get a free energy density, which now depends on a variety of things, but most importantly depends on this T, and that is the result for our free energy density. And this is also very pleasing because it is proportional to N. So in some sense, what it's saying is that each field is sort of independently fluctuating. So these are like independent oscillators, if you wish. Each component is independently fluctuating. So all of them are contributing the same free energy. So there are N of them. So you end up getting N times this. Okay. Okay. So this is how you define and evaluate functional integrals. I hope you will be less intimidated by the term functional integral now than maybe before this lecture. Okay, so let's continue on. So we evaluated this whole functional integral setting u equal to 0 and h is equal to 0. Now you might take issue with that and say, okay, you are throwing the baby out with the bathwater, which is probably true, which is not probably, it's certainly true. So we have to do better. Right? We have to find a way to include the u term in the calculation as well as the magnetic field term, right? So you will see that it's extremely difficult to do that, if not impossible to do that exactly, but we can do that approximately, and this approximation goes by the name of the saddle point approximation. So what I'm going to do now is I'm going to introduce the saddle point approximation for you in an intuitive way by evaluating some one-dimensional integrals. Okay. So the question, of course, we are after is how do we evaluate this 5-4 term, which is critical for getting our phases, etc. Right. So we look at a simpler problem. So imagine G is some nice function. You can take it to be some convex function or something. And what we want to do is we want to compute integral minus infinity to infinity dx e to the minus gx. If we know gx is equal to ax square, then there is nothing to do because that's just the Gaussian integral and you're done. But what if it is not ax square? So suppose the function is something like this. How do we evaluate this integral? Okay, so first thing is that we may not be able to evaluate it exactly. So we have to come up with some close or approximate method to do this. So what would that be? So first is you take this function and look for where it attains the minimum. So let's say that x naught is the point where it attains the minimum. So if x naught is the minimum point of G, around x naught, so around this, it looks like this. G of x looks like G of x naught plus 1/2 second derivative of x at x naught times x minus x naught whole square. The first derivative of course vanishes. That's what gives you the fact that it's a minimum. Okay. So what I'm going to now pretend is that this function looks like a parabola with this value around this. So I'm just going to pretend that that's what is going to happen. And I'm going to just approximate. So I'm going to say that e to the dx e to the minus gx should be approximated by e to the minus gx. So I'm just writing gx equal to this here times integral dx 1/2 g double prime x naught minus x the whole square. And this we can evaluate, and you will see that this integral is exactly this. So I've evaluated this using the known result for the Gaussian integral and then exponentiated the answer. That's how I get this log here. And this is the saddle point approximation. So it is a way of finding integrals of exponentials of functions by going around the minima of those functions and looking at some excursions about the minima and approximating this like a parabola around the minima and evaluating it. Okay. Okay, very good. So now how do we use this idea to evaluate the functional integral when u is not 0? Okay. All right. So I'm back to my Ginzburg-Landau theory with all glory. now. So there is u, there is h, everything is there, and I'm going to make a simple approximation, or a simple, I'm going to state a simple condition. It's not essential to do this, but for our discussion, I'm going to take h to be uniform. What I mean by uniform is that it doesn't depend on space. So h is not a function of x, right? So this is some fixed h. Okay. Now I'm going to evaluate this using the saddle point approximation. So the idea is, this is integral over the space of functions and e to the minus s of phi. So just if you want to connect to the previous slide, think of this as dx and this is s of x. So I have to find the x in that, the coordinate x, where the function became minimum. So here what I have to do is, I have to find the function called the saddle point function phi sp, the field, the emergence, the saddle point field phi sp, which is the saddle point of this functional. Saddle point meaning the extremum point of this function. Okay. How do we do that? So what I have to do is, I have to say that around the saddle point, if I do a variation, so phi sp plus delta phi sp minus phi, the saddle point, must be 0. This is the statement, and this is calculus of variations, which I am sure many of you have seen. And what this will result, it will result in what are called as the Euler-Lagrange equations. And in the context of this problem that we are discussing, the Euler-Lagrange equations will show me that the divergence, the spatial divergence of dl by derivative with respect to gradient of phi minus dl by d phi evaluated at the field, which is the saddle point field, will vanish. So this is telling me that this, the functional will be extremized when phi is the saddle point field. So what will this give us? This will give us a differential equation in general for the saddle point field. The solution of this differential equation will give me the saddle point field. Okay. All right. Now I'm going to invoke the fact that this h that I have is uniform. I'm going to now make a physical claim. It's very easy to prove it, but it's much more sort of pleasing to do the math with, to do the physics without doing the math. So what I'm going to say is that if h is constant, then the uniform solution, that phi saddle point is some constant value called, which I'll call m, and you will see why I'm calling this m, will be the one with the lowest action. How do we see that? So you will see that if I want to minimize the energy here, every instance I have a gradient of the field, I will pay this extra energy. So for any field, if I have extra energy associated with this term, then I will increase energy. So suppose I take the idea that I am looking for solutions where the magnitude of phi saddle point does not vary in space, then certainly having magnitude fixed but the orientation is changing from point to point, like what we saw in the superfluid current flow case, you will see that it will cost this extra kinetic energy, if you wish, right? So what would I want to do? I want to find a solution which is homogeneous in space or constant in space. So that is why I am choosing this. Okay. You can solve the differential equation and show that it is the lowest energy, there is no problem, but the physical argument is perhaps more persuasive. So the spatial variation will cost me additional gradient energy. So I'll leave this as an exercise to you. You can take this equation and show that in the situation where the gradient vanishes, then the saddle point equation is this. So it will be T times m plus u mod m square m minus h is equal to 0, right? But this is exactly the condition set for us for the magnetization, namely the minimum value of L of phi in the Landau theory. So what we see is that the homogeneous saddle point solution is the order parameter of the Landau theory. That's what we are finding. So this is very nice because we have also made connection to our old Landau theory. So the saddle point solution of our Landau-Ginzburg theory is the order parameter that you will get within the Landau theory. And the saddle point value of the action will be V times V is the volume of the system because that's integrated. Phi has picked up the value m, gradient phi is 0. So you just put m here, so this will go away. So it will be T m square plus u m to the 4 minus h times m. That will be the value of this, which is exactly the Landau free energy. Okay. So what we just found is what I am stating here. Landau theory gives the saddle point solution of the Landau-Ginzburg theory, ignoring all fluctuations. Okay. So if you want to understand what is Landau theory in the simple integral example, which I have in the small font here, this is by saying that integral dx g of x is just e to the minus g x naught. So it's like the value at the minimum, exponential of negative, the value at the minimum, that's what it is. Okay. But we know that we have to include fluctuations. So if you stop here, then of course we are doing nothing. I mean, we just recover back our Landau theory from Landau-Ginzburg theory. Okay. So to continue on, what I am now going to say is I have this saddle point, and remember what I did in the one dimensional example. I went x minus x naught. I expanded the g of x about x naught. So I am going to do exactly the same thing here. I am going to take phi of x, some arbitrary phi of x, and I am going to say that any phi of x is now the saddle point value, okay, in our case that is independent of space, so I rewrite that as m, plus a fluctuation zeta of x. This is the fluctuation about the saddle point. So we are bookkeeping our functions, our fields phi of x as the saddle point value plus fluctuations. So it's a way of parameterizing the fields. Okay. So where zeta is the fluctuation about the saddle point field. Now what we are going to do is we are going to take s of phi defined in this fashion, and I am going to put this here, and I am only going to keep quadratic terms in zeta. So this is like my approximation g of x is equal to g of x naught plus 1/2 g double prime x naught plus x minus x naught whole square. So zeta is like x minus x naught. So that's what you have to do. So there is a little bit of algebra involved here, but it's not terrible algebra. You can do it yourself. So you will be able to show that up to quadratic order in zeta, the action s of phi is s of phi saddle point, whatever we have computed in the previous slide, plus an integral over the space, a density now associated with the zeta field. So this is what we call as the fluctuation piece, the fluctuation functional of zeta. So what does it entail? It has this gradient zeta square, which is completely expected, because when I take gradient of phi here, saddle point does not depend, so you just get this gradient, and that will just be gradient zeta square, and t square, because when I write this as m plus zeta and the linear term dies because it's an extremum, and all I am left with is a quadratic term, so that will be just zeta square. And this is the expansion of what I will get when I write phi of x in the quartic term as m plus zeta of x and keep up to quadratic order. So note, you will get two types of terms here. You get a term which is m dot zeta the square, m is the saddle point result, and you will get a term where zeta square, so it's zeta dot zeta and m dot m, right? So the components of m and zeta don't talk to each other here, right? So this is the result you will get. Okay, so this is the fluctuation piece to the action, and what we can now do is we can now define the functional integral approximately. So now what I am going to say is that, you see, I am going to say that my fields are parameterized in this fashion. So it's m plus zeta of x. So this is like changing origin of integration in one dimension. So if I want to do integral dx, remember in the one dimensional problem we had seen x minus x naught whole square. So I can bring the origin to x naught and I can do the integration. So dx will not change under the process. So that's exactly what's happening here. I'm shifting all the fields by a constant m. So d phi and d zeta will be the same. And then s of phi is now replaced by s of saddle point plus sf. So this thing does not depend on zeta. So you can pull that out. So that's e to the minus s phi saddle point. And this is just the functional integral on zeta. And e to the minus sf of zeta is an action which is defined, the fluctuation action which is defined here. Okay. So we have managed to find an approximate expression for this. Now why are we excited about this? You see, when we defined the functional integral with setting u equal to 0 and h is equal to 0, for which we were able to get exact results, see that problem also had an action which was quadratic in phis, right? So this action was quadratic in phi. Now what we are finding is, if you stop at the zeta square order, then this sf is also quadratic in phi and therefore is a quadratic in zeta, sorry. And therefore we can use the same techniques that we used to evaluate that functional integral and use all the known results that we have derived in the previous slides, and we can evaluate this as a function of u and so on. It is approximate. I mean, we are not saying that it's exact, it's approximate. Okay. So this is the saddle point approximation, and it's a good time to summarize this lecture now. So what we are doing is we are analyzing the Ginzburg-Landau theory in this lecture. So we found a way to parameterize the fields using Fourier components in such a way that my field phi of x is aware of the short distance cutoff. So that introduced a momentum cutoff in my momentum space, and the energetics of phi was described by a functional containing 3 parameters. This is our simplest Ginzburg-Landau theory. And what we did was we noted that the Ginzburg-Landau partition function is a functional integral, and by setting u equal to 0, we were able to calculate the functional integral by interpreting the functional integral as an integral over space of functions, and to visit all space of functions, I vary all the Fourier components from all possible values they can take. So that allowed me to compute the functional integral. That was the definition of the functional integral, and because I had set u equal to 0, each of those integrals turned out to be Gaussian integrals, and I was able to get the exact result for the Gaussian integral, and from there I was able to obtain the free energy when u was 0. To get to the functional integral when u not equal to 0, what we did was we introduced this idea called as the saddle point approximation, where we find the value of the field which extremizes the action, and we expand the action about that saddle point, and we keep only up to quadratic order terms in the fluctuations, and that again reduces to a problem that is very similar to the one by where we calculated with the u equal to 0 with the phi theory. So it will be a quadratic theory, and that will allow us to compute the functional integrals. A very important observation that we found that we made during the process is that the saddle point solution of the Ginzburg-Landau theory is the good old Landau theory which ignored all fluctuations. So you can see that it systematically improves on the Landau theory by adding fluctuations to some order, right? In this case, quadratic. Okay. All right. So in the next lecture, what we are going to do is we are going to evaluate the free energy as a function of t, u, y, all of those within the saddle point approximation. So the natural question, the big suspense is, will this resolve the critical exponent puzzle? And I am sure you will not want to miss the next lecture. So I'll see you in the next lecture. Thank you.